Hello, my name is James Davis. I've decided to do the recursive backtrack maze generator algorithm. The recursive backtracker, just like most of the other maze generation algorithms I found, creates a big tree graph. I turned in one of the implementations that I did for an algorithm a week, and it was very efficient and successful, but it had one flaw. Due to the recursive nature of the implementation, I could only generate a 130 by 130 cell maze. It wouldn't go any bigger. So let me show you what I mean. Now, just for reference, this maze is a 25 by 25 maze. Some of the squares were added in between the actual cells of the maze generating algorithm just for aesthetic reasons. Anyway, show you an example here. This is a 4 by 4 maze. Obviously, this is an exaggeration, but you get the idea. So this over here represents the stack, and each coordinate here in the stack represents the method being called, the recursive method being called. So this is the recursive method. Randomly, it's going to decide to go, we'll say, to the right. Nothing exciting happens here. You notice as it moves, it pops another method calls another method, pops it onto the stack while it's calling it, pops another activation record onto the stack, keeps going, and here it dead ends. What the recursive algorithm does, it checks all the neighbors. It says I don't have any available spaces to go to, so that method is done running. So then it goes back to the method before it, checks, doesn't have any, goes back to the method before it. As you can see, it's freeing up stack memory. So it gets here, it does have a neighbor that it can go to. So it's going to go up, add one to the stack, go over, add one to the stack, go over, add one to the stack. And this is where I ran into the problem trying to generate 150 by 150 cell maze, is stack overflow error. So as you can see, the stack overflowed. For testing purposes, I added this little feature that would count the longest path of the graph. And I found that for a 130 by 130 cell graph, which was the biggest I was able to do, the longest path was averaging 5,500 cells in length. The longest one I got was 6,979 cells. That means this recursive function was being called about 7,000 times and added to the stack that many times. Now, I don't know how much of the stack each instance of this method takes up, and I don't know how big my stack is. I don't know how many methods it could handle, but for a larger graph, it was pretty easy to understand that it would overflow. So for the purpose of this presentation, I started thinking of some options that I had that would allow me to make a bigger graph. I thought I could put a limit on how deep the recursion went, but that would restrict the graph unnaturally. Probably could result in an incomplete maze. For example, this little area over here might not get filled in if I did that, because it might be beyond the reach of that restriction that I imposed. So I thought of another option. Some compilers I know for optimization will take a recursive function and change it into a loop. And that, if I did that, it would still allow for a buffer overflow if my array was too big and my list of occupied coordinates were too big, but the stack overflow problem would be solved. So that's what I did. I took a list and I added the occupied coordinates to that list, and then I have the array of cell objects as indicated here by this graph, and that's the most memory that I'm going to need to use, save a little bit of overhead. That method's only going to be called one time though, so that's not bad. This is what that looks like. Here we have, for a 16 cell graph, we're going to have 16 different times that it's going to run through. And what it's going to do, it's going to add, each time, it's going to add to this list of coordinates, and keeps adding, keeps adding. We're going the same way we tried to go last time. We stop here, and this is where we're at 2, 0. What this one does, if it has to go back, it will allow the for loop to run an extra time, so it decrements the counter that the for loop uses so that it can run an extra time, as we'll see. So okay, it's going to decrement it again, so it's still only going to run 9 more times. Okay, that one still doesn't have, still hasn't gone to a neighbor, so it's only going to run 9 more times, but now it has an available neighbor above it, so it's going to just add that to the next element on the list and keep going through the list that way. And we're going to go, and as you can see, we're already further than we were before. Our stack hasn't overflowed yet. We get to the end here, then we're at 3-3. We're going to back up. It's going to let it go one more time. So it's only going to do 3 more times that for loop, but each time it goes back, it's going to let it go an extra time so that it can account for all the empty spaces on the graph. Here it's got a neighbor. It's going to go to that neighbor, go to the neighbor, go to the neighbor. Graph is complete. This implementation worked like a charm, but is a very slow charm. But it still worked. I was able to create a 500 by 500 cell maze, but it took the computer 6 minutes to do that. So for comparison, a 130 by 130 maze out of 10 runs, the recursive method generated a maze in less than 1/10 of a second each time, and the non-recursive implementation took over 1 second each time, up to 1.5 seconds. 500 by 500 cell maze is roughly 16 times that size of a 130 by 130, which is the most I could get with the recursive method. But after 6 minutes, I decided I didn't want to try another one. I was satisfied with that 500 by 500. That was my goal, was to get one that could do that, since the recursive couldn't even do 150 by 150, and I didn't want to squander my youth waiting for a maze to generate. So now let's look at some pseudocode here. First we'll look at the cell class. As you can see, this one has 4 Boolean attributes that tell if it can go a certain direction, 4 Boolean attributes that tell if it does go a certain direction, and 1 that tells if that cell is occupied or not. And then it's got a constructor. This just marks the edges. If it's on the left, then it can't go left. If it's on the right, it can't go right. One thing I did try, because this class is, fair size, I tried to optimize this other recursive implementation. I tried to replace my array of these objects with Boolean variables and just fill it up. I wasn't concerned with direction. I just wanted to fill it up. The stack still couldn't hold it all, so that indicated that the method was being called more times than the stack can handle, and not that my data structure was too large. So we'll look at some pseudocode here. This non-recursive recursive method, the loop recursion method, I guess, is passed in 2 parameters, an x and a y coordinate. That's the starting point. I made it to where you can start anywhere on the graph. Then we got to declare some variables first. We have the Boolean to tell if we've moved this turn, this iteration through the for loop. We've got a list of directions, just 4. Each one appears once and exactly once. A list of occupied cells called path list, index for that list of occupied cells, I, and the total number of elements in the maze, size. So first of all, we start by adding that initial coordinate to the path list, and then we mark it as occupied. Then the for loop's going to run only the amount of times as there are elements in the maze, so size times. We get a new random list of directions each time. We say that we have not moved yet each time, as you can see down here. Then if I is within the bounds of that path list, I did have some errors trying, I was going too far below, and it would get negative, and that didn't work. So anyways, if it is, then x and y become the coordinates at I in that path list. This makes sense a little bit later whenever we start moving back through the list, as we saw in our example above. So anyways, we check the neighbors of the current cell, and then for each direction in the list, we have 4 different if statements. For brevity, I just did one here, which is applicable to each of the 4 directions. If the neighbor in that direction is not occupied, so it is available, then we're going to indicate in this object here that the cell does go in that direction. We're going to add that new cell coordinates to the path list. We're going to mark that one occupied. We're going to set I to the newest coordinate added to the path list in case we have to start moving back. And then we're going to set did move to true because we did move, and then we're going to stop checking the other directions. We don't want to move left and up at the same time. So if did move is false, so if we didn't move, none of those directions worked because none of the directions had an available space next to it. Then and if we haven't filled the board yet, so if we're still less than size, then we're going to run this loop one more time. So we're going to decrement that counter in this for loop. And then we're going to decrement I, so we're going to move backwards through path list. And then we'll come back up here. D is a new random list of directions. Did move is false. X and Y are now this new coordinate in path list. We're going to check the neighbors, and we're going to go through that size times. So, anyways, that's my presentation. Was very successful once I did the non-recursive version of this recursive method. If there are any questions or comments or constructive criticism you have, anything that would have made this presentation more interesting or better, more informative, please feel free to let me know. Thank you very much and enjoy the rest of this maze.